Welcome to another academy. In this video, we are going to discuss about direct products. So here, first we are going to see what do you mean by external direct product, internal direct product, and what is the relation between external direct product and internal direct product, and how to find the order of a given element in the direct product of groups, and finally, how to find all abelian groups of given order. Okay, so these are the things we are going to discuss in this video. Let's start with the definition of external direct product. Let A and B be any two groups and let G equal to A cross B. Then the elements of G will be of the form set of all ordered pairs A comma B, where the first element A belongs to capital A and B belongs to capital B. Okay, so for this collection, we define operation. How do we define the operation? If you take any two elements A1, B1 and A2 belong to A2, B2 belong to G, then the product of the two elements A1, B1 into A2, B2 is defined to be A1, A2, comma B1, B2, where this product is with respect to the operation defined in capital A. And here for the second element B1, B2 is there, no, this operation is with respect to B. Here already we have taken A and B are two groups, no, so they may be having their own binary operation. So for the first element we follow the binary operation defined in A, and for the second element we follow the binary operation defined in B. Both the operations need not be the same. Okay, the set A may have one binary operation and B may have some other binary operation. Okay, even though they have different binary operations, we can define the direct product like this. So with respect to the product which is defined here, this G forms a group. Okay, and it is called external direct product of A and B. Okay, next one, internal direct product. Let G be a group and N1, N2, etc. N and B normal subgroups of G. Okay, so from a group G, I am taking the collection of all normal subgroups. Okay, such that G satisfies these two conditions. It is G can be written as product of N1, N2, etc. up to Nn, and every element of G can be written as uniquely written as G equal to M1, M2, M3, etc. Mn, where each Mi belong to Ni. Okay, this again here with respect to this operation, G forms a group, and this G is called what? Internal direct product of N1, N2, N3, etc. up to Nn. So if you look at these two definitions, here I have defined the external direct product with a product of only two groups. It need not be restricted to two groups. It may be extended to n groups also, like A1, A2, etc. cross An, right? So here we have defined internal direct product. The difference between these two is, here we are starting with two different groups A and B. From the groups A and B, we arrive at a new group. Okay, from an external set, external group A and B, I am arriving at a new group G, and here I have a group. From that group I am considering its normal subgroup, so I am not going anything outside the group. Within the group itself I am finding normal subgroups such that the given group can be written as product of its normal subgroups. Okay, so that every element of the group can be written as uniquely written as product of its elements in the normal subgroup. So this is external direct product, and this is called what? Internal direct product. Right. Next one, G is the internal direct product of N1, N2, etc. Nn. Then intersection of Ni with Nj equal to E, and it is commutative. That is, if you take any Ni and Nj belong to the sets, then Ni into Nj equal to Nj into Ni. So this will give you the unique representation for every element of capital G. This property gives you the unique representation of G belong to capital G. Okay, then let G be a group, and suppose G is the internal direct product of N1, N2, etc. Nn. and let me take T equal to N1 cross N2 cross etc. Nn. Then G is isomorphic T, isomorphic to T. What I am coming to say here is, see, first I am taking one group and I am writing it as a internal direct product of its normal subgroups. Okay, so this point is clear. Next, what I am going to take is, you forget about this G, just you consider these groups n1 n2 n3 etc up to n, these are groups, no? So if I am given with n different groups, I can define external direct product from these n groups, isn't it? So that external direct product I am taking it as capital T. Okay, so I am having a set of n groups with which initially I define one internal direct product and then external direct product. Then these two groups G and T will be isomorphic to each other. Okay, so whenever you have internal direct product and external direct product for a group, they will be isomorphic to each other. Okay, structurally they are different. Here they will be like ordered pairs. No, here it is not like that, product of the number, so it will be simply a single number only, but still they are isomorphic to each other. So hereafter we are going to just to say direct product. We are not going to use the word either internal or external because they are isomorphic, no? So it may be either internal or external direct product. Since they are isomorphic, just we are going to make use of the word direct product, right? So let's see some of the results based on these. Every finite abelian group is a direct product of cyclic groups. Next one, let G be a finite abelian group of order P1 power alpha 1, P2 power alpha 2, etc. Pk power alpha k, where P1, P2, etc. Pk are all distinct prime numbers and alphas, all the powers are positive powers. Then G is a direct product of P1, capital P1, P2, Pk, where each Pi is a P silo subgroup. So here what we are concluding is, that is this internal direct product we have written, no, that is every group is written as a product of its normal subgroups. The possibility is defined here. See, if a group is of finite order means we can write its power as, we can write its order as power of prime numbers, distinct prime numbers, no? So take any finite abelian group and write its order as powers of distinct prime numbers. Then we know here P1 power alpha 1 is a prime factor which is dividing order of G, no? Definitely we know it has a P1 silo subgroup, and similarly it has P2 silo subgroup of order alpha 2, etc. It has Pk silo subgroup. Okay, all the P silo subgroups are normal subgroups only. So we can write this G as what? Direct product of P1, P2, etc. up to Pk. So this is what this theorem states. Okay, then next one, let G be an abelian group of order P power n, right? Then G can be written as A1 cross A2 cross etc. Ak, where each A is a cyclic group of order P power ni, where n1 greater than or equal to n2 greater than or equal to nk, right? So this theorem states, in the previous one what we have seen, G is an abelian group of order P1 power alpha 1, P2 power distinct prime numbers, product of powers of distinct prime numbers. Here suppose G is an abelian group of order P power n, then still we can decompose it as direct product of what? K number of its subgroups. Each one is cyclic with order P power ni, the same prime number with different powers. The powers form a sequence, no, n1 greater than or equal to n2. This sequence is nothing but partition of your n, because if you add all the powers n1, n2, etc. nk, you will get it as n, no? So this n1, n2, etc. nk, they are nothing but partitions of n, and they are called invariants of the group G. Okay, next, two abelian groups of order P power n are isomorphic if and only if they have same invariants. So just like that you can't say, if you have two abelian groups of order P power n, just like that you cannot say they are isomorphic. What you have to check? Whether the invariants are same or not. What do you mean by invariants? The power of the prime number P. Okay, right. Then the number of non-isomorphic, this is an important result which we use for doing problems, these two things. See, if you want to find the number of non-isomorphic abelian groups of order p power n, then it is equal to the partitions of n. You know what is meant by partition? Okay, so for any group, any abelian group of order p power n, the number of non-isomorphic abelian groups is equal to partitions of n. Suppose if my group is not of order p power n, it is of order p1 power alpha 1, p2 power alpha 2, etc., pr power alpha 2, pr power alpha r. Then what about the number of non-isomorphic abelian groups? In that case, number of non-isomorphic abelian groups is equal to p of alpha 1, p of alpha 2, etc., p of alpha r, where each one is nothing but this is partition of p alpha 1, this is partition of alpha 2, etc., partition of alpha r. Okay, I will do some problems based on this. So before that, we will see some more results. See, Zm cross Zn, you know what is Zm and Zn, no? Modulo groups of order m and n. Zm cross Zn is cyclic always, and it is isomorphic to Zmn if and only if m and n are relatively prime numbers. Otherwise, we cannot have this result. So, cyclic and isomorphic, both of the things achieved only when m and n are relatively prime to each other. For example, you see Z2 cross Z3. Here this 2 and 3 are relatively prime numbers, no? So, it is isomorphic to Z6 and it is cyclic. But Z2 cross Z2 is not isomorphic to Z4 because see this 2 and 2, they are not relatively prime numbers, no? Okay. And suppose G is a direct product of A1, A2, etc. up to AN. Then how to find the order of any element in G? Then order of the element in G is equal to, see this A1, A2, etc. AN are all elements of AIs, no? That is A1 belong to capital A1, A2 belong to capital A2. So they will be having their own orders in the respective groups, no? Find the LCM of R1, R2, etc. Rn. What is this Ri? Ri is nothing but order of AI in AI. Find the LCM, that will give you order of the required element in the direct product. Okay. So let's see some examples. Find the order of 8, 4, 10 in Z12 cross Z60 cross Z24. See, 8 is an element of Z12, 4 is an element of Z60 and 10 is an element of Z4. First, let us find these orders. Now, order of 8 in Z12. How to find? It is nothing but, see, this is Z12 group, no? 12 by GCD of 8, 12. Okay. What is GCD of 8, 12? 4, no? So, 12 by 4 equal to 3. So, order of 8 in Z12 is 3. Next, order of 4 in Z60 equal to 60 by GCD of 4, 60 equal to 15. Next, order of 10 in Z24. 24 by GCD of 10, 24 is equal to 12. So, order of 8, 4, 10 is equal to LCM of these three numbers 3, 15, 12. What is LCM? 60. So, order of this element is equal to 60. Next one, order of 2, 6 in Z4 cross Z12. Now, order of 2 in Z4 equal to 4 by GCD of 2, 4 equal to 4 by 2 equal to 2. And order of 6 in Z12 equal to 12 by GCD of 6, 12 equal to 12 by 6 equal to 2. So, LCM of these two orders 2, 2 equal to 2. Therefore, order of 2, 6 in Z4 cross Z12 is 2. Okay. Next, we are going to find the abelian groups up to isomorphism. See, if M divides order of G and G is a finite abelian group, then G has a subgroup of order M. This you can consider as a converse of Lagrange's theorem. The famous Lagrange's theorem in group theory, what does it say? If you have a group, then order of any subgroup divides order of the group. But the converse is not true there, no. That is, order of any subgroup divides order of the group, but the converse, what is the converse? If a number divides the order of the group may not have a subgroup of the given order. So, when the converse will be true? The converse is true when the group is finite abelian. If the given group is finite abelian, then it will have subgroup of order which are all divisible, which are divisors of order of G. Okay, so this is like converse of Lagrange's theorem. Next one, let M be a square-free integer. Square-free integer means if you factorize M into prime factorization, there should not be any square terms. Okay, then every abelian group of order m is cyclic. This is also, see, we know every cyclic group is abelian, but the converse is not true. Every abelian group need not be cyclic. So that converse, this is just for a converse. So if you have a abelian group, if its order is square free, then it will be cyclic. So these two are very important notes. Okay. Now let's see the abelian groups up to isomorphism of given order. So find the abelian groups of order 8 up to isomorphism. First, 8 is equal to 2 power 3, no? So this is power 3, no? This is, so write the partitions for 3. What are the partitions? 3, 2 plus 1, 1 plus 1 plus 1. So there will be 3 abelian groups up to isomorphism. So what are they? Here 3, no? So this, for this z 2 power 3, z 8. Next one, 2 comma 1 means z4 cross z2. 2 means what? Z square. So z4 cross product with 1 means what? 2 power 1. So z4 cross z2. This is z2 cross z2 cross z2. Okay. So these are the different groups up to isomorphism of order 8. And order 32. See, 32 can be written as 2 power 5. So 5 has 7 partitions. 5, 1 plus 4, 2 plus 3, 2 plus 2 plus 1, 1 plus 1 plus 1 plus 2, 1 plus 1 plus 3 and 5 times 1. Once if you write the partition, it is easy to write. This corresponds to z 2 power 5, that is z 32. And this corresponds to z2 cross z 2 power 4, that is z 16. This corresponds to z2 square, that is z4 cross z2 cube, what is that? z8. And this corresponds to z2 square cross z2 square cross z2. And this corresponds to z2 cross z2 cross z2 cross z2 square. And this corresponds to z2 cross z2 cross z2 cube. And this corresponds to z2 cross z2 cross z2 5 times. Okay. So these are the 7 different abelian groups up to isomorphism of order 32. Next one for order 720. See, the 720 prime factorization is 5 power 1, 2 power 4, 3 power 2. So product of powers of 3 distinct prime numbers. So the number of abelian groups up to isomorphism will be partition of 1 into partitions of 4 into partitions of 2. There is only one partition for 1, and for 4 there are 4 partitions, and for 2 there are 2 partitions. So 1 into, just I am not multiplying the powers, I am finding the partitions of the powers. Partition of 1 is 1, partitions of 4 is 4, partition of 2 is 2. So 8 different abelian groups. Okay, right. So how will you write? First you write z5 cross z16 cross z9. Next one, this 5 cannot be factorized furthermore, no? So in all the 8 different cases, z5 will be the same. Next, z16 can be factorized, no? How will you factorize z16? 8 into 2, 4 into 2 into 2, 2 into 2 into 2 into 2. Okay. Next one is 4 into 2 into 2. So in one set you factorize this 16, in another set you factorize this 9. Okay, z3 cross 3 and z9. Okay, so various combinations you can write like this also, and you can pair them all together. Okay, I hope you all understand this video. Thank you.